Hi, so today we're going to talk about inverse functions. Let's just look at notation. So f of negative 1 is not an exponent, that's inverse notation. So recall that f of negative 1, or f inverse, is not equal to 1 over f. So f inverse is not equal to 1 over f. That means the inverse of the function f. Let's just review a little bit of properties of a function. So every function has a domain. It's going to be the set of x values that we can actually put in the function, and it'll have a range, which is the set of y values of our function. So a function will take an x value from its domain, it'll do whatever its job is, and it'll give us back a y value. So what an inverse function does, if it exists, is it's going to take that y value and give back the original x value. So since we're putting the y value into our inverse function, the range of our function becomes the domain of our inverse function. And the domain of our function is now the range of our inverse function. So not all functions have an inverse. A function does have an inverse if it's what we call one-to-one. Okay, so if we look at this definition here, it says that a one-to-one function, or sometimes this is called an onto function, passes the horizontal line test. So remember, a function passes the vertical line test, but a one-to-one function, or a function that actually does have an inverse, will pass the horizontal line test, meaning that every horizontal line will intersect the graph at most once. But graphs are not an accurate way to show whether a function is one-to-one or not. So there is a more precise way that we can show whether a function is one-to-one or not. If the y values are different whenever the x values are different, then the function is one-to-one. But with this definition, we have not equal to. It's really hard to work with things that are not equal. So it's much easier to use the alternate version, which says that the x values are equal whenever the y values are equal. Okay, so what that means is that if the y values are the same, then the x values have to be the same. So in example 1, we have this function 2x minus 7, and we want to use this definition to verify that the function is one-to-one. So what we're going to do is we're going to just suppose that the y values are the same. So we're going to suppose that we have y values that are equal. Okay, and this is for any x sub 1, x sub 2 that are in the domain of our function. So we use this weird e for element of, or in the domain of our function. Now all we have to do is algebraically show that if these y values are the same, the corresponding x values have to be the same. So we're going to go ahead and rewrite f of x sub 1 with the definition here of our function. So this becomes 2 times x sub 1 minus 7, and then our f of x sub 2 becomes 2 times x sub 2 minus 7. Okay? So algebraically, we have this equation. We can add 7 to both sides to get 2 x sub 1 is equal to 2 x sub 2. And then dividing both sides by 2, I have x sub 1 is equal to x sub 2. So we're done. We said, okay, if we have any y values that are equal to each other, the corresponding x values also have to be equal. But I need to conclude. So the conclusion is, therefore, f is 1 to 1. So oftentimes, instead of writing therefore, because mathematicians are lazy, we'll use these 3 dots, which mean therefore f is 1 to 1. Okay, and that's it. So we want to verify that this is a function, a one-to-one function, by also looking at the horizontal line test. So what I'm going to do is I'm going to do a real rough sketch, nothing fancy, of my function f. So it's a line, it's going to pass through 0, negative 7, and 7 halves 0. So if I draw my line, okay, and this is my function f, passes through 7 halves, 0, and 0, negative 7. Okay, so remember, it will pass the horizontal line test if every horizontal line passes through at most one point. And I can clearly see that any horizontal line I draw will pass through at most one point. Okay, so that's it for example 1. What happens if a function is not 1 to 1? How do we show that a function is not 1 to 1? Well, to show that a function is 1 to 1, for all y values that are equal, all x values have to be equal. To show not 1 to 1, all we have to do is come up with one example where the y values are the same and the x values are not. So if we look at example 2, the function is a parabola. It opens down. I know it's not going to pass the horizontal line test. So all I have to do is come up with one example. So f of 0 is equal to f of 4. Is that true? F of 0 is 0. F of 4 is also 0. So these y values are the same. But notice that the corresponding x values are not the same. And that's it. I've shown that my function is not 1 to 1 by coming up with one example where the y values are the same but the x values are not. And there's infinitely many points I could have used. Okay? So my conclusion, the function is not 1 to 1. All right, so it's not 1 to 1. So let's do another quick sketch. Again, nothing fancy. This is a parabola. It's opening downward. It looks like 0 and 4 will be my intercepts. And at 2 is where my vertex is. Again, you could just plug this in a calculator if you don't want to waste your time finding points. Okay, so definitely not 1 to 1. So what I want to do now is I want to restrict this so that I can get the largest possible interval, which makes a 1 to 1 function. So the logical thing to do is to just cut this parabola in half. So if we look, and this would be, ooh, what is this point? Is this 2? Oops, sorry. Don't want that. So I believe this is 2. So if I look to the left of 2, this interval which is the interval from negative infinity. Oops, sorry. Keep forgetting to change my thickness. It goes from negative infinity to 2. Gives me a 1-to-1 function. And if I look to the right of 2, this interval from 2 to positive infinity gives me another 1-to-1 function. Okay, so these are the largest possible intervals that correspond to 1-to-1 functions. Well, let's just say you have two functions and you'd like to verify to see if they are inverses of each other. And that brings us to theorem 7.1. It says to verify that functions are inverses of each other, first of all, their domain and their range has to switch. Okay, so they have to switch domain and range. And the second thing you have to check is to see that if you compose them in both directions, okay, what you put in is what you get back out. What you put in is what you get back out. Okay, so let's look at example 3. We have these two functions, f and g. And I want to verify that they're inverses of each other. Okay, so the first thing I want to do is I want to verify that their domain and their ranges switch. So notice that for my function f, the domain of f is all real numbers. Or in interval notation, it would be from negative to positive infinity. Because the function is x cubed, I can put in any x value, it's fine. And also notice that the range is negative to positive infinity. Now if you're not sure, go ahead and get out your graphing calculator or graphing device and graph x cubed, and you'll clearly see what the domain and the range is. So now let's look at the domain of g. So it's the cube root of x, which means I could put in any x value, any real number, and I'm fine. And then I also get back the range, which is negative to positive infinity. So something to note is domain and range match up. So that's the first thing we need to check. The second thing we need to check is that if we compose them in both directions, not just one, both directions, what we put in is what we get back out. So let's compose f of g of x. So that's going to be f of g of x is the cube root of x. So when we put that into our function, we get the cube root of x, quantity cubed. So remember that if the root and the exponent match, they cancel. So this is just x. So what we put in is what we got back out. Now we have to compose in the other direction, g of f of x. So that's going to be g of, and f of x is x cubed. So we're putting x cubed into our function g. G is the cube root function. And again, exponent root match, they cancel. So what we put in is what we got back out. So our conclusion is, since the domain and range is switched, and since when we compose them both directions, what we put in is what we got back out, f and g are inverses. All right. So let's go ahead and look at the next page. Let's say that we have a function. It's 1 to 1, and we want to find the inverse. Not a problem. Okay. If you have a 1 to 1 function and you want to find the inverse, the first thing you want to do is replace the function notation with y, and then solve the equation for the x. You may need to restrict the x value. Last thing you want to do is, once you've solved for x, interchange your x and y, and then you can replace y with function notation. But I have a problem with example 4. So example 4 says to find the inverse of our function f, but f is not 1 to 1. It's a parabola opening upwards. It does not pass the horizontal line test. Okay? So let's do a little quick sketch here. We have this parabola. When x is 0, y is -4, so it does something like this. And I'm going to pretend like this is -4. So it looks like I'm going to have to break this up into two functions. To the left, I'll call this f sub 1 of x, and that would be x squared minus 4 for x values that are less than or equal to 0. And then to the right of the vertex, I'll call this f sub 2. So f sub 2 of x is equal to x squared minus 4 when x is greater than or equal to 0. Alright, so now I have these two 1 to 1 functions. I can find the inverse. So let's just look at this first one, f sub 1 of x. We need to replace the function notation with y, and then solve for x. So x squared is equal to y plus 4. And now when I square root both sides, I have to remember that it's plus minus the square root of y plus 4. Okay, so remember for f sub 1 of x, the x values are less than or equal to 0. So I'm going to choose the negative. Okay, and might as well interchange my x's and y's right now. So this is my inverse function. I can now replace y with f sub 1 inverse of x. Now if we look at f sub 2 of x, the process is going to be exactly the same, except for when we get to here, x equal to plus or minus the square root of y plus 4, in this case we're going to choose the positive. And exchanging x and y, I get y is equal to the square root of x plus 4, and I'm going to replace y with inverse function notation. Oops, sorry, 2. Alright, so those are my two inverse function for my original function f. Something interesting to note is if we were to graph these, f sub 1 inverse is going to be a lower half of a parabola. Sorry, my sketches are kind of bad. and then f sub 2 is the upper half. So if we put these two together, this lower half and this upper half, what we get is a parabola that opens to the right. And if you look at the original function, it was a parabola opening up. So we just took this parabola and we flipped it. Now at the very bottom here, just want to make a comment that if a function is continuous, its inverse will also be continuous. Well, let's look at the next slide. Let's say that we have a function and we want to graph a function and its inverse. Well, that's pretty simple to do because all we have to do is exchange x values and y values. So for example 5, part A, it says graph the function and its inverse. So first of all, I'm going to graph the function because that's what I have. That would be x squared plus 1, but I'm only concerned with x values that are greater than or equal to 0. Okay? So if x is equal to 0, y is 1. If x is 1, y is 2. And if x is 2, y is 1, 2, 3, 4, 5. Alrighty, so here is my function. So again, it went through the point 0, 1, 1, 2, and 2, 5. So to graph the inverse function, I exchange x's and y's. So my inverse function is going to go through, 1, 0, 2, 1, and 1, 2, 3, 4, 5, 2. So this is inverse, and this is my function. Okay. Now something to notice is that these are mirror images of each other across the line y equal to x, which is what we call the axis of symmetry. Okay, so I've graphed my function and its inverse, so this was part A. And now let's go ahead and look at part B. So in part B, we need to find the derivative of the function and evaluate it at 1. And then we have to find the derivative of the inverse and evaluate it at 2. Well, finding the derivative of my function is pretty straightforward since I have x squared plus 1 as my function, derivative is 2x. And then evaluating it at 1, we get 2. I'm going to have to do a little bit more work if I want to find the derivative of the inverse function because I don't have the inverse function. So my first step is to find the inverse function. I'm going to replace the f of x with y. And then we're going to do what we did in the previous example. We're going to solve for the x. So x squared is equal to y minus 1. And since we're only concerned with x's that are greater than or equal to 0, when I square root both sides, I take the positive square root. So let's go ahead and replace x's with y's. Okay. So our inverse function, f inverse of x, is equal to the square root of x minus 1. So now I have to find the derivative of my inverse function. So if I take my inverse function and find the derivative, that's going to be equal to 1 over 2 times the square root of x minus 1. So when I evaluate the derivative of the inverse function at 2, we get 1/2. Okay, so remember, to go from a function to its inverse, you exchange the x's and y's, which means geometrically we're flipping across the line y is equal to x. So what do you notice about the derivative? Okay. Now remember, this point on my function was the point 1, 2. Okay. We put in this x value, 1, and we got the derivative was 2. The inverse function passed through the point 2, 1. We put the corresponding 2 into our inverse function, right? The derivative of the inverse function, and the derivative is 1/2. So what's interesting to note is that the derivatives are flipped. They are reciprocals of each other. Which brings us to this theorem, which is theorem 7.3, the derivative of the inverse function. So let's say we have a function that's differentiable and it has an inverse. So if our function, if we take the derivative of the function and we evaluate it at some x value, we just have to make sure that that derivative is not equal to 0. Then the derivative of the inverse function evaluated at the corresponding y value is going to be equal to 1 over the derivative of the function. Okay, so something to note is this x sub 0, y sub 0, this is a point on the function f, not on the inverse function. Okay, so if we take this point and we evaluate the derivative of the function at the x value, it's going to be the reciprocal of the derivative of the inverse function on the y value. So something that comes from that theorem is these other two equations that you're free to use if you need to. And that falls from theorem 7.3. So let's go ahead and look at example 6. And we'll go ahead and see how we could use this. So let's say our function is the square root of x plus 1. And we want to use theorem 7.3 to find the derivative of the inverse function at the point 516. So I have a problem here, and the problem is the point 516, this is not a point on my function. And the theorem specifically states that we have to have a point on our function. Because notice, if I put 5 in for x, I don't get 16 back for f of x. This is actually a point on f inverse. Okay? So the point on f that corresponds to it would be the point 16, 5. That's the point on my function f. So this would be the x sub 0 and the y sub 0 in theorem 7.3. Okay. So I need to find the derivative of my function f, and that's going to be equal to 1 over 2 times the square root of x. If I evaluate this derivative, when x is equal to 16, that's going to be 1 over 2 times the square root of 16, which is 1 over 8. All right. So again, sorry, this is part A. So if I use the theorem, the derivative of the inverse function evaluated at the point 516 means we're going to put 5 in to the derivative, and it's going to be equal to 1 over the derivative of the function evaluated at 16, which is 1 over 8, or in other words, 8. So part B says, verify part A by directly computing the inverse function and then find its derivative. Oh, which I don't want to do, but we'll go ahead and do this. First of all, replace f of x, with y. Solve for x. So we have the square root of x is equal to y minus 1. So I need to square both sides to get the x by itself. And then I have to exchange my x's and my y's. And this would be my inverse function. So once I have my inverse function, then I would compute the derivative. And the derivative is, chain rule, 2 times x minus 1. Oh, that's it. Okay, so when I evaluate this derivative, when x is equal to 5, it's going to be 2 times 5 minus 1, which is equal to 8, which is exactly what we knew would happen. Okay, so in my face-to-face class, we sometimes, if we have time, do some in-class problems. So we can use these as extra review problems for this class. Okay, so let's go ahead and look at number 1. We have this function, square root of 2 minus x, and we want to use the definition to verify that it's 1 to 1. So remember what we do, right? Sorry, I scribbled here. What we need to do is assume that our y values are the same. So we have f of x sub 1 equal to f of x sub 2, okay, where x sub 1 and x sub 2 are just elements in the domain of my function. Okay, so if I replace f of x sub 1 with the definition of this function, it's the square root of 2 minus x sub 1 equal to the square root of 2 minus x sub 2. And then when we square both sides, I have 2 minus x sub 1 is equal to 2 minus x sub 2. So subtracting 2 from each side, and then dividing by negative 1, I have x sub 1 is equal to x sub 2. So therefore, my function is 1 to 1. So now let's go ahead and graph our function. Remember, it was for x values that are less than 2. So at 2, we have, 0. I apologize for the screen. At 1, 2 minus 1 square root of 1 is 1. When x is 0, we have square root of 2. I don't know what that is. What about 2? Or negative 2. If x is negative 2, then this would be a positive 2. So it looks like my function kind of does something like this. So the inverse function, we exchange x's and y's. So if this is the point 2, 0, and here we have 1, 1, and then at this point here this was negative 2, 2, then my inverse function is going to pass through 0, 2, 1, 1, 2, negative 2. And it'll go down this way. Okay, so this would be the inverse function. And here I have my function. So if we wanted to find the derivative of f evaluated at 1, the derivative of my function is equal to 1 over 2 times the square root of 2 minus x times the derivative of what's underneath the square root, which is negative 1. Okay. Or in other words, negative 1 over 2 times the square root of 2 minus x. So if we evaluate the derivative, if we evaluate this derivative at 1, it looks like it's just going to be negative 1/2. So instead of computing the inverse function and then finding its derivative, I'm just going to use theorem 7.3. If I take the derivative of the inverse function and evaluate it at 1, it's going to be the reciprocal of negative 1/2, or negative 2. So this last piece, this part 4, it says to evaluate the derivative of the function at 2, and then evaluate the derivative of the inverse function at 0. So notice that the point 2, 0 is on the function, right? So we could use the theorem, but there's a problem here. If you put 2 into the derivative of the function, it's undefined. Okay? So f prime of 2 is undefined, and I use DNE for does not exist. So what that means is if I were to find the corresponding derivative of the inverse function at 0, that also does not exist. Okay? So a little bit of a trick question there. And something just to remind you of is that typically when we're talking about differentiability of a function, we do not include endpoints anyway. Okay, so that's it.